This section we're going to be going over derivatives of polynomials and exponential functions. So previously when we were trying to find the derivative of a function, we were using the limit definition of the derivative, and it was kind of tedious and the calculations were pretty long. So now when we're going to be asked to find derivatives of certain functions, we're going to have these certain rules, starting with this section, that are going to make this a lot shorter for us so we don't have to use that limit definition derivative. So starting with the derivative of a constant function. So we know a constant function, if we graphed it, it is a horizontal line. So the derivative of any constant function, d dx of c, is going to be 0. So remember, we're finding kind of like a slope function with the derivative. So if it's a horizontal line, the slope is always 0, so the derivative will be 0. So let's go ahead and see this example. Let's find the derivative of f of x equals 7. Well, 7 is obviously a constant, so f prime of x, the derivative, equals 0. And if we graphed it, we know it's a horizontal line at 7, at y equals 7, and that slope is always 0 no matter what, so the derivative is 0. So that's going to be the easiest derivative, and the second easiest is going to be the derivative of a linear function. So we know linear functions can be put in the form y equals mx plus b, where m is the slope, b is the y-intercept. We also know that linear functions have a constant slope over their entire domain. So that means if we take the derivative of a linear function, d dx of mx plus b, it's just going to equal the slope. So the derivative of a linear function is just going to be m. And once again, derivative is going to tell us the slope. And since a linear function has a constant slope, that's going to be the derivative of the linear function. And also remember that a linear function, hopefully we know this, has an exponent of 1, highest exponent of 1. Okay, so let's see a couple examples here. Let's find the derivative of the following functions. F of x equals x. So that's a linear function with a slope of 1, right? Because there's a 1 out front of that x, so that means that is the derivative. The derivative of that function is 1. So no matter where we look at on that line, the instantaneous slope, or the slope at a certain point, is going to be 1. Next one, we have y equals negative 2x plus 6, and we have the derivative y prime. This is linear. The slope here is negative 2, which means that is the derivative. The derivative is negative 2. Y prime equals negative 2. And just remember, we could write this as dy dx for the derivative. Either one would be completely fine. Okay, so now moving on to a rule that maybe gets a little bit harder. This is called the power rule, and this is going to be the derivative of a power function. So a power function, recall a power function is going to be in the form f of x equals x to the n, where n is a real number. So it is just x raised up to some real number. So the real number is in the exponent. And if we want the derivative of that, that's when we know how to use the power rule. The power rule tells us the derivative of x to the n equals n times x to the n minus 1. So the way that I'm kind of going to be reading this off when I'm doing these questions is you have x to the n, you're going to multiply the exponent out front, and then you're going to subtract 1 from the original exponent. Okay, so that's how I'm going to kind of be reading this. This is the power rule, very, very important. So let's do a couple examples. Let's determine the following. If f of x equals x to the 6th, let's find the derivative. So finding the derivative, it's going to be power rule, right? Because we have a power function x to the 6th. We're going to bring the original exponent out front. When I'm going to be saying that a lot, bring it out front. That means we're multiplying it out front. X, it's 6 times x. And then we subtract 1 from the original exponent. So this derivative is 6x to the 5th. Obviously, you don't have to do this intermediate step. Just do 6 minus 1 in your head. Okay, next example. We want to find DDR of r to the 1,000. So we want the derivative of r to the 1,000 with respect to r. So once again, power rule. So it's going to be bring the exponent out front, multiply it out front. That's 1,000r. Now subtract 1 from 1,000 for the new exponent, which is 999. And that's all we have to do for that one. Notice that there's no, we don't need to write any notation for it because it just is telling us to find DDR of that function. Next one, we have y equals x squared. We want to find y prime. So we have y prime. So we have power rule. Bring down the 2. Subtract 1 from the original exponent. 2 minus 1 is 1. We don't need to write the exponent of 1. So this is just y prime equals 2x. So the derivative of x squared is 2x. Okay, now let's make them a little bit more difficult. Let's find the derivative of y equals 1 over x. So before we do that, we need to rewrite this as a power function, which means we need to write it as x raised up to some variable, or rather x raised up to some number. 1 over x can be rewritten as x to the negative 1. So that's how we have to write it. So now we can find dy dx. And it's going to be the same idea as before. Bring down the negative 1 and subtract 1. Negative 1 minus 1. We have to be a little bit careful. We end up getting negative 2 for the exponent. So you could leave it like that. That's completely fine. I'm going to write it like this. Negative 1 over x to the positive 2, just so we remember some exponent rules with making it positive, putting it in the denominator. Next one, we want ddt of 6 over t cubed. So once again, before we do anything here, we need to rewrite this as a power function. 6 over t cubed would be rewritten as 6t to the negative 3. Okay, so for this one, we're going to multiply the negative 3 out front. 6, we have 6 times, well, I'll write it like this. I'll do the negative 3 first. It really doesn't matter. Negative 3 times 6t. Negative 3 minus 1 is the new exponent. So that gives us negative 18 t to the negative 4, which once again we can leave it like that, or we can write it as negative 18 over t to the positive 4. And 2 more for this one. We have ddx of 2 over the square root of x. Just like before, we need to rewrite this as a power function. The square root of x we know is an exponent of 1/2. So what we can do is, instead of having it x to the 1/2 in the denominator, we make it x to the negative 1/2 in the numerator. And then we just perform power rule, bring down the negative 1/2. Then we need to subtract 1 from that new exponent. That gives us just negative 1, because negative 1/2 times 2. So negative 1x. And then negative 1/2 minus 1 is negative 3/2. So maybe write this as negative 1 over x to the positive 3/2. And just like I mentioned before, if you can do the steps in your head, do them in your head. You don't need to write down this step if you can do that math in your head. Okay, last one for this particular type of question. Y equals 1 over the cubed root of x squared. We want to find the derivative. Before we do that, let's go ahead and rewrite this. We can rewrite that cubed root of x squared as x to the 2/3. And rewriting that as a power function, x to the negative 2/3. Okay, so now the derivative, power rule. Bring down that negative 2/3. Subtract 1. So negative 2/3 minus 1 is going to be negative 5/3. So make sure you know how to add and subtract fractions. You're going to need to be able to do that in order to do a lot of these questions. And let's just rewrite this one also as negative 2 over 3 times x to the positive 5/3. So even though I'm writing these with positive exponents, just kind of keep in mind it really doesn't matter too much. You could leave it just like this right here with the negative exponent. Okay, so now for some derivative rules. So we have some rules that we kind of already just did, like the constant multiple rule. So these rules are going to be kind of creating new functions from old functions like addition, subtraction, and multiplication. So first one, the constant multiple rule. If we're taking the derivative of a constant times a function, you can essentially bring the constant out front and then do the derivative of the function separately and then multiply them afterwards. And the next one is the sum rule. The sum rule is if we are doing the derivative of two functions being added, we can do the derivative separately and then add the results. It's kind of like distributing the derivative to both of them, if you want to think of it that way. And then same thing with the difference rule. If you're doing the derivative of something, two functions being subtracted, do them separately and then subtract the results. So let's do a couple examples. The first two were hopefully kind of easy because once again we kind of already did some examples like these. So d dx of 3x to the fourth. So that's going to be, let's do this one a little bit quicker. We bring down the exponent of 4. 4 times 3 is 12. Subtract 1 from the exponent, we get 12x cubed. So hopefully you can kind of do them quickly in your head like this as you start to get used to them. Next one we have d dx of negative x. So technically this would be that constant multiple rule. We would bring out the negative 1 times the derivative of x. We know the derivative of x is 1. That's negative 1 times 1, so negative 1. Hopefully you don't have to do all that because this is just a linear function. The slope is negative 1, so we know the answer should have been negative 1. Skip right to the answer. Next one, a little bit harder. We want the derivative of x to the 8th plus 12x to the 5th minus 4x to the 4th plus 10x cubed minus 6x plus 5. We're going to do all of these individually because they're separated by addition or subtraction. Okay, so let's go ahead and do them all individually here. The derivative of x to the 8th, we know that that's going to be 8x to the 7th. That is the power rule. And next we have the derivative of 12x to the 5th, so plus. Multiply the 5 out front. 12 times 5 is 60. Subtract 1 from the exponent, so we get 60x to the 4th. Next one, minus the derivative of 4x to the 4th. 4 times 4, we get 16. Subtract 1 from the exponent. Negative 16x cubed. Next one, 10x cubed. Multiply the 3 out front. We get 30. Subtract 1 from the exponent. And then the next one is a constant term. The next one is a linear term. So it's negative 6x. The derivative is negative 6. The derivative of that last constant term is 0. So there is our derivative for this function. So just term by term, power rule, and then linear term, and then a constant term. Okay, in the next example, we want to find the points on the curve, y equals x to the 4th minus 6x squared plus 4, where the tangent line is horizontal. So tangent line being horizontal, obviously that's going to be a line that's like this, horizontal line. So we have to think, what kind of slope does this line have? Horizontal lines have a slope of 0. So that means we have to find the derivative and then set the derivative equal to 0 and solve it for x. So let's go ahead and find the derivative. So we have y prime, and this is just going to be power rule. So we get 4x cubed minus 12x, and then the derivative of the constant is 0. And now we're going to take this and set it equal to 0. So we set it equal to 0, and then we get 4x cubed minus 12x equals 0. And we can factor out a GCF of 4x. We'd be left with x squared minus 3. And then we set all of these equal to 0, both of these equal to 0 separately. 0 product property, 4x equals 0 gives us x equals 0. And x squared minus 3 equals 0 gives us x squared equals 3. Take the square root of both sides, we get x equals plus or minus the square root of 3. So these are our x coordinates, and I'm just going to cheat a little bit. And I'm going to say let's just plug those back into the function to get their y coordinates. So plug each one of those back into here and evaluate each one to get the y coordinates, but I'm not actually going to do it. But if we did do it, we should get our three answers: negative radical 3, comma negative 5, and 0, comma 4, and radical 3, comma negative 5. So these are our three ordered pairs. And then you can see the graph here, and you can see the 3 points here, here, and here. And you can see how they have a horizontal tangent line at those points, meaning the slope of the tangent line is 0. Next example, the equation of motion of a particle is s equals 2t cubed minus 5t squared plus 3t plus 4, where s is measured in centimeters and t is measured in seconds. We want to find the acceleration as a function of time, and we want to know what is the acceleration after 2 seconds. So we're given position function, we're looking for acceleration function. So we need to use these two facts here. We know that velocity equals the derivative of position, and then acceleration is the derivative of velocity, which is the second derivative of position. So that means to find acceleration, we need to take two derivatives of that function. So let's go ahead and take the first derivative. I'll call it v prime, v. V is s prime, which is, so taking the derivative here, that's going to be power rule. So it's going to be 6t squared minus 10t plus 3. And now we need to take the derivative of this new function to get acceleration. So we can, if you really want to, you can write it like this. You can write acceleration equals v prime equals s double prime. You don't have to write all that. I'm just doing it just so we know all of these relationships. So taking the derivative here, we get 12t minus 10. And that is actually our acceleration function. So I'm going to label it a of t. You don't have to put the a of t part. You can just put a. It is 12t minus 10. Okay, and the second part of this question said, what is the acceleration after 2 seconds? So that's just time equals 2. So that's going to be evaluating a of 2. That is 12 times 2 minus 10. And that gives us 24 minus 10, so 14. So we need to think of the units here, because if we have units, we should include them. So we know our answer is 14, so what are the units? So the position function was in centimeters, time is in seconds. Every time you take the derivative, when you're starting with something in centimeters, you are going to be dividing by another seconds. So we start with the units of s. That's going to be centimeters. We take the derivative of that and get velocity. That's centimeters per second. We take the derivative again, get acceleration. That's going to be centimeters per second times another second. We obviously don't write that. We write second squared. So these little brackets represent dimensions, so I'm just writing the units for them. Okay, if we took the derivative of acceleration and got jerk, that would be centimeters per second cubed, and so on. So this is going to give us 14 centimeters per second squared. And I'm just using an S to denote seconds rather than SEC. Okay, so we just went over the derivative of a constant function, the derivative of a linear function, and then the derivative of essentially any polynomial and any power function using the power rule. Now we're going to be doing the derivative of exponential functions. So we're going to be doing the derivative of functions f of x equals b to the x. So now the variable is in the exponent. So if we try to do this using the limit definition of the derivative, and we were taking the derivative of b to the x, here's the limit definition of the derivative. What we would do is plug in f of x plus h minus f of x all over h. That would give us this second line right here, b to the x plus h minus b to the x all over h. So it gets a little bit tricky. What we have to do is use exponent rules, and we chop up this portion. B to the x plus h can be rewritten as b to the x times b to the h. So once we get to this line right here, we see that we can factor out a b to the x. If we factor out a b to the x, we end up with this second last line right here. And this limit here only depends on h, right? As h goes to 0. This term does not have an h in it, so we can take it and write it out front. So that's where we get this last line right here, and that's going to be kind of where we start this next setup here. So what we got is that when we took the derivative of f of x equals b to the x, we got f prime of x equals b to the x, which is itself, and then we get this other portion right here. So that limit value is actually the derivative of the function evaluated at 0. So this portion right here is actually f prime of 0. So that gives us this relationship right here, which is what we just said, that if you are starting with the function f of x equals b to the x, then we have the derivative is f prime of 0 times the original b to the x. So the question is, how the heck are we supposed to know f prime of 0? Because we need the derivative for it, but we don't really have the derivative yet because that's part of the derivative itself. So we'll get into a different way to do these a little bit later. So we're going to go with this definition, and we are going to find this f prime of 0 using a table. So let's say we were using b equals 2 and b equals 3. This would give us our two functions, f of x equals 2 to the x and f of x equals 3 to the x. Now if we were using that limit definition of the derivative portion from right up here, and we were using it with a b of 2 and a b of 3, we would end up with these values. So what we're doing is saying, let's let h get closer and closer to 0. So we're plugging in values into here where h is getting closer and closer to 0, and we're evaluating them, and we're getting these values for each one. So we can kind of make a guess to see where each one is going. It looks like this one maybe is near 0.69, and this one is maybe going around 1.09 something, but we'll just say 1.10ish for now. So we can see where those two values are going. So that's what we're going to say that's what they are approximately, which is what we say right here. So for b equals 2, it looks like this value is about 0.69. For b equals 3, it looks like this value is about 1.1. So what we're going to do is we're going to use that definition that we just said before. The derivative of b to the x equals, well, let me rewrite that. I'll say for f of x equals b to the x, we know that f prime of x, the derivative of that, is f prime of 0 times b to the x. So here are those two definitions using a b value of 2 and a b value of 3, and we have f prime of 0 for both of them right here. So the whole reason why we're using a 2 and using a 3 here is because both of these values, 0.69 and 1.1, there's definitely a value of 1 between those, right? So we could have chosen a value for b between 2, between 3, such that this value, f prime of 0, would have equaled 1. So that means f prime of 0 would equal 1 for some function b to the x. And this number is the number e. So I just put it here, maybe a little bit shorter and easier to understand. F of x equals b to the x will give you a value of f prime of 0 equals 1 when the base is the number e. So what that means e is the number such that the limit as h goes to 0 of e to the h minus 1 all over h equals 1. So that is why this number e is so important. It has, one of the reasons why, it has the derivative. You'll see another reason why in a second, but if you take the derivative of it and plug in 0, you get out a value of just 1. So what does that mean? That means if we have the function y equals e to the x, and we put a nice little dot when x equals 0, that means the slope of this tangent line equals 1. And hopefully we remember that e, like we mentioned several times right now, e is just a number. It's about 2.718. It's irrational. It goes on forever, never repeats itself, similar to pi. So just remember that e is approximately 2.718. But we're always just going to write it as just e. Okay, so that brings us to another important property of e, the derivative of the natural exponential function. So e to the x, the function y equals e to the x, is the natural exponential function. If we take the derivative of it, it equals itself. So the derivative of e to the x is just e to the x. So basically, we did all of this kind of confusing part using a b value of 2 and 3 and using limits just to show that the derivative of e to the x is just e to the x. So make sure you have that memorized. So let's do an example. Let's say if f of x equals e to the x minus x, let's find f prime and f double prime. Okay, so let's start with f prime. F prime of x is the derivative of this. So we do it term by term here. The derivative of e to the x is just e to the x. The derivative of negative x is negative 1. So f prime of x equals e to the x minus 1. And now let's do f double prime, the second derivative. So now we're taking the derivative of the first derivative. The derivative of e to the x is e to the x. The derivative of negative 1 is 0 because it's a constant. So f double prime of x is just equal to e to the x. So let's do one more example here. We want to know at what point on the curve y equals e to the x is the tangent line parallel to the line y equals 2x. So before we even do this, let's just draw a very rough sketch here. So here is the graph y equals e to the x. Now let's see the graph of y equals 2x. Y equals 2x will look something like that, going through the origin with a slope of 2. So we want to see what point on y equals e to the x is the tangent line going to be parallel to y equals 2x. So maybe just by taking a quick glance at it, we should say maybe this point right here, because if we did this tangent line, it might look something like this, where it's parallel to the line y equals 2x. So we're going to be looking for this x coordinate right here that makes those two lines parallel. So now we have to figure out how do we do that. So what we have to do is we need to find the x coordinate on y equals e to the x that has a tangent line with the same slope as this line, right? Parallel lines means that the lines have the same slope. And anytime you think slope, that's pretty much going to mean taking a derivative. So we want the x coordinate that has a tangent line with the slope of 2, right? Y equals 2 to the x is linear. 2 is the slope of that line. So with a slope 2. So that means we need to find y prime and solve y prime equals 2. So we need to take the derivative. That'll give us the slope equation and set that slope equation equal to 2. And then solve for x. That'll tell us the x values when the slope is 2. So we have the function y equals e to the x. We know that the derivative of e to the x is itself. So now we're going to set y prime equal to 2. So e to the x equals 2. And then we say, okay, how do we solve for x here? We have to remember solving exponential equations. We would technically take the ln of both sides. That's x equals the ln of 2. So we have to remember the little conversion here. If we have y equals b to the x, to solve that for x, we get y equals log base b of y. In this case, the base was e. So if you need to review exponentials and logarithmic equations like that, then make sure you do that to solve these types of equations. And ln of 2 is about 0.693. So it seems like it should be correct with the graph that we drew. My graph is just a real rough sketch, so it might not look completely correct either. Okay, so that is the x value that makes, or that has a tangent line that is parallel to the line y equals 2x. Okay, so that is it for this section.